we're going to hear from Pow.Bio and their senior manager, R&D, Magdalena Stoeva. Magdalena.
All right. Good morning, everyone. My name's Maggie. I'm here from Pow.Bio to talk to you a little bit about how we're reimagining biomanufacturing and some of the work we're doing on using predictive modeling, using continuous fermentation to solve some of the challenges that I think we're all acutely aware of in biomanufacturing. And so I like to start with this slide, and I think we're all familiar with this pipeline, you know, the biomanufacturing pipeline. And so you start with this grand idea, you figure out how to make it using biology, you engineer your strain, you build some sort of baseline process. That's all what I refer to as, you know, the front end of the pipeline. And there's a lot of innovation that happens here, and there's a lot of money that gets poured into this front part. And then we move into the second phase. And I think that's where a lot of projects hit a roadblock. This is where you have to process develop. You have to optimize your process. You have to scale and tech transfer your process. And then, of course, at the end, you have commercial deployment. And there's a lot less innovation that happens here, historically a lot less money. And this is the part of the pipeline that really matters. So you really need to hit your cost targets to make it to the end of that. So this is where Pow.Bio focuses, and I'll tell you a little bit about how we do that. We have this three-pronged approach, and so I'll tell you a little bit about each of these pillars. The first one is continuous fermentation. And so we use continuous fermentation to bring down costs of manufacturing, and we have a special approach to it that kind of mitigates some of the classical risks that people think of when they think of continuous fermentation. So that's pillar one. Then we have a kind of a software in the middle here, Sophie, and that's our optimization software. And I'll tell you a little bit more about that as well, but that's this idea that you can rapidly optimize processes, rapidly, you know, go through this huge black space of all the parameters you can test to get to your optimized process so that you can scale it. And then the third pillar is CASI, and CASI is our model predictive controller. And again, I'll have some slides towards the end to tell you a little bit more about CASI, but the idea there is that CASI will help you transfer to a different facility, will help you scale up, and will help you run your fermentation at your commercial scale, you know, a kind of akin to the self-driving fermenter. Okay, and so put that all together, you have these highly productive continuous fermentations that are optimized, that can scale, and then that can run really efficiently over long periods of time. Obviously, you can see how that's going to help with your make you CapEx, OpEx light. And then, of course, all of that feeds into our own internal knowledge base, which we then use to feed back into each of those pillars. Oopsies, sorry. So, a little bit about our continuous fermentation platform. Like I said, we're trying to solve for the usual things that people think of when they think of continuous isn't going to work, and that's really solving for strain mutation and solving for contamination. And so the way we approach this is we actually run a two-chamber system. We separate growth in its own fermenter from production. And so you have a growth fermenter that grows happy cells that are not producing. So it's a very stable system. Those cells get transferred to a production chamber. That production chamber is optimized for production. Very little growth happens there. In that way, it's contamination resistant. And then the last little bit here is this cell retention loop. And that essentially retains biomass to the extent that you want to retain it while continuously permeating out product. And that allows you to really reach your maximum fermenter volumes, your maximum cell densities, and therefore your maximum productivities really early on in the fermentation. You know, in fed batch, usually you don't get there till the very end. So you can bring that up and then run at that for really long periods of time. And so what does that look like? So this is some data that we have from one of our bacterial processes, making a small molecule. And on the y-axis is total product that you've made, and you can see kind of how the fed batch compares. So you can run multiple successive fed batches, but for the same period of time, for the same fermenter, you get 5 times more product in our continuous system. And we've replicated these kinds of results across multiple different platforms. So we worked with many different hosts, making anything from small molecules, proteins, and we consistently see that our continuous system outperforms the fed batch system. And we can plug those numbers into our TAs, and we get significant benefits of significant cost reductions from that. Okay, so that's continuous manufacturing. That was our first pillar. I want to tell you a little bit about our approach to optimization. I think we all know it's like a little bit of a scary place. And I think traditionally you have, one tank, 1 point, 1 data point per week. And so very low data density. We leverage our continuous platform to temporally multiplex different conditions. And so we get much higher data density. We can pair that with our smart algorithm. That's SOFI. So we pair that with SOFI, and SOFI can rapidly and efficiently explore this multi-parameter space to find process optima. And so the graph you see here is a real-life deployment of SOFI, and you can see the space we're exploring is the X and Y axis, right? So pH and temperature, that's the 2-dimensional space we're exploring. And the Z axis is how much better you are, in this case on titer, relative to kind of the baseline fed batch process. And so, so if he was able to find, okay, this is your optimum pH, this is your optimum temperature. We've deployed this in 3-parameter space, we've deployed this in 4-parameter space, and we really can rapidly kind of explore that parameter space to find the optimal process for you. So that's all nice and great. We can hopefully get through that PD stage a lot quicker. And what I want to emphasize here is we generate a lot of data by running these kinds of fermentations. And that data feeds into our third pillar. And if you remember, our third pillar is CASI. And CASI is our model predictive controller. And so what are we trying to solve for? I guess biology is really hard. I think it's hard at any scale. It's not very intuitive. There's huge differences between tanks. There's differences between how people run those tanks. There's differences in batch to batch variation, even if you're already at your manufacturing scale. And so it can be non-intuitive to really know how to run consistent, high productivity, the exact same fermentation over and over again. And that's why we developed CASI. And so CASI can generate reference data sets for you so that you can see, okay, this is how my fermentation is going to look like in this tank, in this location. You can also do in silico hypothesis testing, in silico optimization. You can simulate deviations, see the effect of various deviations, automatically flag deviations, and in dev, course correct after those deviations. So what should we do now that we've experienced a deviation to still hit our final target? And so that's our automated control. And so I want to show you a little bit how we used CASI in our most recent project. And our most recent project is this scale up. So we had a process in-house, a continuous fermentation, that we wanted to tech transfer to a facility in Europe. And at the same time, we wanted to scale it up to 3,000 liters. And we had some internal milestones that we wanted to hit. So we wanted to make sure we were going to maintain our productivity that we see in-house. And we wanted to run for 2 weeks, 300 hours. And of course, we had like one shot on goal. We wanted to all get it done in one shot. And so we did all of the things that we thought we needed to do to set ourselves up for success. We pre-validated everything that we could possibly think of. We delivered a very thorough tech transfer package. Our partners, our CMO partners, said it was the most thorough tech transfer package they've ever seen. And there was still a lot of surprises. And so I want to walk you through 2 examples of some of these surprises and how Cassie helped us essentially manage them. And so one of them was that, at the last minute, we decided to run in a different tank at a slightly lower volume. And at this lower volume, the oxygen transfer rate of this reactor wasn't going to be sufficient to feed our fermentation at the rate that we wanted to feed at. And so we were going to have to feed at a lower rate. And that's kind of a big deal. And so we were a little bit stressed about it. And we asked Cassie, okay, well, in this hypothesis testing mode, tell us what's going to happen at this lower feed rate. Do we need to go back to the drawing board? Do we need to change the tank? Do we need to change the volume? And Cassie said, well, actually, at this lower feed rate, you're still going to get 94% of your total product. So don't sweat it. Run your fermentation, and it'll be okay. And we did just that. We ran at this lower feed rate. We ran for 300 hours, and that was absolutely fine. And so in this way, Cassie did this mini optimization of the feed rate at our new scale. We, of course, also had some surprises on the cell retention side of things. So I told you we kind of used cell retention to amplify our process. And when that system was all ready and finally set up, the team looked at me and said, well, what do you want to run the permeation, right? What rate do you want to run this continuous extraction at? And I was like, well, I don't know, because so many things had changed. The reactor had a very different evaporation rate, but on top of that, so many things had changed from our original process. And so we plugged this into Cassie, and Cassie said, you should run with, 5 liters an hour, and that's what we ended up doing, and that held stably over the next 300 hours. And so again, kind of, there was a deviation, that was flagged, and then we corrected, okay, this is going to be our permeation rate that we need. Okay, and so the result of all that is that Cassie really helped us navigate the uncertainty. So it removed a lot of the guessing that we would usually have to do. And you can see, again, we have total product on the y-axis, and the fed batch in the same tank for the same amount of time is in yellow, and our run is in green. And so we had a very, very successful tech transfer. We had a very successful scale to the 3,000 liter, and we made 3 times as much product as we could have made from this tank running in fed batch mode. And so I think that really goes to show the power of continuous, especially when you pair it with some smart data-driven practices. Okay, and then I want to end on this slide and give a little bit of time for questions if people have questions. But I want to bring it back, to kind of that first slide that I showed, which is, the biology, the biomanufacturing pipeline, and really highlighting this second phase, process development, scale up, manufacturing. And hopefully I've convinced you at least a little bit that Pow.Bio's continuous platform can really run at these super high efficiencies. We have software tools that can help you navigate optimization, that can help you navigate scale up, and that really at the end of the day are going to bring you to market faster. They're going to get you to market. They're going to get you to your cost targets faster. Okay, and so with that, I'll leave it on this slide, and thanks.